So this is Kevin Rice. I'm a field crop entomologist at the University of Missouri, and I'll be talking to you about the brown marmorated stink bug and some of the things we learned about the invasion in the mid-Atlantic area and what we might expect as the invasion front moves into the Midwest. And again, I apologize that I can't be there in person. I had some family issues come up. I'm actually an alumni from Ohio State and a huge Buckeye fan, so I was actually hoping to go up there and visit, but unfortunately that didn't happen. So to begin with, brown marmorated stink bug, as you probably already know, is an invasive herbivore. It was unintentionally introduced to the United States sometimes in the 1990s, and it's spread pretty quickly across the eastern seaboard, and it started to cause real agricultural problems in the late 2000s. And the way to identify this species compared to our native stink bugs is if you look at the antenna, you have this white and black banding that's very distinct, and there's also this banding of white and dark shading on the abdomen edges. So that's how you can identify it compared to our native species have just solid brown antenna most of the times. So it's an extreme generalist. It feeds on hundreds of host plant species and causes severe economic damage, and it has a high dispersal capacity. So females on flight mills, we've tracked them. The average, they can fly up to 5 kilometers per day. At extreme events, when we force them to fly on these little flight mills in the lab, they can actually fly 80 kilometers. So they can move around, and they feed on lots of different host plant species, but they typically sort of hang out on the edge of the crops, and we'll talk about that a little later in this presentation. So this is just the life cycle here we're going to go through very quickly. The eggs are laid on the underside of leaves. They're usually initially light green, but they turn white. There's usually 28 eggs per egg mass. And this is the first instar larva. The first instars actually do not feed on the plant. They feed on the egg shells. They're picking up some of the bacteria that the mothers provided for them so they can digest their food. This slide is just showing you the different instars, and the reason why I'm showing this is just to show that each instar has that banding on the antenna, so you can see that distinctive white and dark banding to identify the invasive brown marmorated stink bug compared to the native stink bugs. So as I said, it feeds on a lot of crops, causes massive damage. It feeds on vegetables, fruits, field crops, and ornamentals. And is moving between those crops and causing damage, and that can be problematic for our control and our management because even when you spray a field, they move back in from neighboring fields, and we'll talk about that in a few. So damage in field crops can be pretty intense. They feed on corn and soybean. They discolor the kernels and lower the quality. It's not unusual to see this high of a population on corn. They prefer the R3 and R4 stages. In soybeans, they can actually cause pod abortion, and they also feed on later stages of soy, so they reduce quality. Additionally, they have this stayed green syndrome. So as I said, they're an edge species, but when they're feeding on the edge of soybean fields, they cause the plants to fail to go into senescence, and that actually causes an additional problem when it comes to harvest. So most of your field is ready to be harvested, but you're losing the edges that are not dried down yet. So that causes additional problems in soybean. And in the mid-Atlantic, you can see this really just destroyed our established IPM programs. This is a calendar from one of our growers, just to show you that they basically had to move to calendar-based sprays, and then they started having problems, of course, with secondary pest outbreaks and additional costs for managing them. So our initial way to monitor BMSB, we're using these black pyramid traps. So these are visually attractive. They have a top funnel trap on top with some kill strips, and the Asian literature had suggested that BMSB might be cross-attracted to the Asian stink bug, and we knew that pheromone, so we were able to use that in the trap initially. However, it didn't really attract BMSB throughout the entire season, and that's problematic for monitoring. The USDA did a bunch of tests, and they eventually synthesized and identified the aggregation pheromone produced by BMSB itself. And now we have these commercially available lures with this aggregation pheromone and these synergists. So you add these components together and you get higher captures. These are available through several companies that you can purchase online. Initially, we wanted to see if we could increase trap captures and the sensitivity to brown marmorated stink bugs. So we did some things where we were putting these lights on top of the pyramid traps. We were using different colors. This was very expensive and cumbersome. We have to run lines of electricity into that's what it kind of looks cool at night. That's what it looks at night. We compared trap capture. We saw that there was some preferences. White light was the most attractive, but blue lights were more specific to BMSB, so you get reduced trap captures of non-targets. But again, for growers, you guys are growers, no one really wants a big black pyramid trap. No one's ever going to use a light trap probably in their field. So more recently we started to use different designs of traps to see if we could use a cheaper trap and possibly one that didn't interfere with grower operations. And we tried a whole bunch of these trap designs. Some of them are smaller, you can hang in trees or put on the outside borders of your we did find some interesting correlations that these yellow sticky cards, they captured less stink bugs on them than the big pyramid traps. However, they were correlated with the black pyramid traps. So that means that they capture less, but that might be okay for monitoring. So now we're moving towards a simpler and a cheaper way of capturing. Again, so they are correlated with pyramid traps. You can hang them up. They're a lot cheaper and a lot easier with. Currently, Kelly Tillman and I, Kelly Tillman at the Ohio State University, we are investigating whether we can use the clear sticky traps to monitor BMSB in field crops. So we've shown some at the USDA has used these in orchards, and they found that there's a correlation again between them. And the reason why we want to move the clear traps is because you reduce the non-target counting, right? So in 2018, Kelly and I did field studies in Missouri and Ohio, and we placed these clear sticky traps in fields, and we found that it does look like they are correlated with sweep net captures. Nymphs and adults are captured on them, and we're working out the math now, and we're going to repeat this in this current field season that's coming up. And hopefully we're also going to be trying to put these on the outside borders of fields instead of in the field. So it'll be a quick and easy way to monitor BMSB in your field crops that may give some support decision making. One of the questions we had early on was, when you put these lures out, how far are you attracting stink bugs into those traps? So if you place a trap, how far away do you have to have another trap? How far is that attracting distance? And to quantify this, we did some mark, release, recapture experiments. And we did this in a what we would call a food desert. We did it in a big grass field because we didn't want any of the host plants attracting the bugs. And we placed a single trap in the middle of the field, and then we marked BMSB with all these different color fluorescent powders. So these are fluorescent powders that glow in the dark. We can simply just spray these powders in a solution mixture on different bugs, and then we can these bugs at different distances. So we release some blue bugs at 10 meters, and some pink bugs at 20 meters, and some yellow bugs at 40 meters, and then so on. And we look at the trap captures, and if you can determine, well, you don't catch any more yellow bugs, you can start to use some math and some calculus to figure out how far that plume distance is actually attracting BMSB traps. And what we found is that the plume area, the attractive distance of that when there's no other host plants available, is about 3 meters. And that doesn't sound too exciting, but the thing is that BMSB is moving around so much that basically results in that the trapping radius to catch bugs is about 121 meters. And you will capture about 4% of the population within 4.8 hectacres with one trap. So these traps are very effective, and this is using the clear sticky traps. So basically, the take-home message is the traps really work, and you can actually relate the number of the population in your field to the trap population. So as I said, they're moving around these fields, they're moving between crop systems, and when I was at Penn State, one of the first questions we had was, can you determine if your landscapes around your your field would influence damage? So we wanted to see if certain crop types in your neighbor's field or your field would influence damage. And we also wanted to look at where if there was a difference in geographic climate, basically if there was anything to do with degree days that might influence damage rates or the invasion front spread. So to investigate this, we actually worked with some of our industry partners at a processing tomato plant, and we did this because instead of us going to fields and sampling data, which is very labor intensive and requires a lot of funding, we were able to work with our industry partners where they're bringing in these trucks from several states, and these are harvested tomatoes, and they grade them in this little grading house before they go to the processing plant, and they're looking for mechanical damage or bacteria rot, and they let us slide in there and actually quantify the damage of BMSB in each truckload, and we had the location and the GPS coordinates for each farm in that coming in. And basically we found those farms on using the GPS, and we created a 250 meter buffer around each of those fields, and then we categorized the landscapes within those fields, whether it was agricultural, whether it was forest or orchard or other. So other is basically waterways or urban developments. And then we did a whole bunch of fancy landscape analysis where we had 56 variables, and we wanted to see if any of those variables were associated with damage in those fields. And surprisingly, out of all those 56 variables, there was only 2 that predicted damage in your field. And one of those was forest mean patch edge, which basically meant the amount of forest edge on the side of your field increased damage in latitude because of the invasion front. We were expecting that. So if you go further south, you have more damage. That's basically what the graphs are showing here. The more forest edge you have, the more damage you have, and if you go south, you have more damage as well. So what does this mean for Ohio? This is a map. I think this is probably done by a lot of Celeste Welty's work. It's highly distributed throughout the state, and these are the reports of where it is occurring, positive identifications through time. And basically, from what I said before, it moves around a whole lot. It has the ability to fly several kilometers in a short amount of time. I would be willing to say that it's present throughout the entire state of Ohio. In Ohio, it's currently classified as a nuisance pest, and that means that it's mostly homeowners that are complaining about this. And that is what happened in the Mid-Atlantic initially. The first infestations were in homes. That's where they overwinter, and that's where we got calls from people saying there was a problem with this new stink bug. And then as the population built, it moved into agriculture, and that's what we're seeing in Ohio and much of the Midwest. Right now it's in people's home, and we would expect the pattern to follow, that we would see it in agriculture very soon. One of the interesting things we saw was there seemed to be a gradient initially. The red states are where we were having extreme economic damage, and we noticed there seemed to be a gradient that some of our growers in the northern part of Pennsylvania didn't seem to have as much problems with BMSB. But if you went just a few hours south to somewhere like Lancaster, they were having a whole lot of economic damage problems. And we started to think, was there some sort of pattern going with generations? Maybe there was one generation in the north and 2 generations in the south, and that would cause increased damage. And we did a whole bunch of tests with the cages where we put out BMSB in cages and monitored their development. And sure enough, it seems that there was more generations the further south. And when I got to Missouri, I was very interested in this. There's a model available on Penn State's website where you can go take weather data from anywhere in the United States and shove it into this model, and it will predict how many generations you'll have of BMSB in that specific area. So I did this for 2017 when I first moved to Missouri, and it predicted that there would be only one generation per year in Missouri. And I started presenting this to growers at extension meetings, and they said, hey, you weren't here in 2017, but that was a very, very normally cold summer and spring, so your model might be wrong. And they were absolutely right. I reran the data set with using 30 years of weather data from those specific places in Missouri, and sure enough, the growers were right, and we would expect actually 2 generations per year in Missouri for BMS. And I'm basically showing you that to show that there is huge variability in the population of BMSB in space and time. So in 1 year, you might have a lot of damage, and then the next year, the population just doesn't seem as high. And the same thing happens with locality. So some farms will experience intense economic damage 1 year, and the next year they just won't. But down the road, their neighbors might be experiencing damage the next year. So it's very hard to predict. We still don't understand what is actually driving a lot of this variability. However, one of the things that might be happening in the mid-Atlantic especially is that we're getting some biological control. So this is the samurai wasp. This was unintentionally introduced to the United States, and this is a small little wasp, and the females will actually sting stink bug eggs, primarily brown marmorated stink bug eggs, and she will lay her eggs inside there, and then the wasps develop, feeding on the egg. And in Asia, brown marmorated stink bug is not a huge economic pest because samurai wasps can control up to 90% of the population, so they're a very, very effective predator. So it was first detected in Maryland in 2014, but has rapidly spread throughout several states. And in fact, some of my colleagues are complaining because they can't collect enough BMSB in the field now to maintain their laboratory colonies. So basically, we think that this samurai wasp might be knocking down the populations now of brown marmorated stink bug. It's not going to be the silver bullet. It's not going to get rid of them, but it might slow them down and reduce economic damage in our crop systems. This is the current distribution of the samurai wasp. So it's in multiple states. It's spreading, and we hope again that it'll be spread. It is present in Ohio, and that it will help us control as BMSB populations increase. That this may knock them down. One of the issues we had with when we started tracking the samurai wasp is that most of the individuals or the individual wasps were found in forest systems, and that's not too surprising because brown marmorated stink bugs do feed on hardwood trees. They're one of the only stink bug species in the world that can feed directly through the hardwood, and they have this strong association with wood. So they feed on woody trees, and they also overwinter in the woods. So it's not surprising that the samurai wasp might forage there. But I was a little concerned that we were not finding this wasp in any of our agricultural systems. So to scout for samurai wasps, we put out BMSB eggs on sticky cards. We leave them out there for 24 hours, then we take the eggs in and we see if anything emerges. And we were finding them in the forest, but not in ag. Concerning. So this previous summer, I worked with Ann Nielsen at Rutgers University, and we wanted to compare the foraging preference of samurai wasp among habitats. So we set up this study where we put BMSB eggs on sticky cards, and we put those cards up in some peaches, and we also put those cards up into some of the forest edge. And then we marked laboratory samurai wasp with this fluorescent powder. So this is powder that glows in the dark under UV light. So you can take a flashlight, a UV flashlight, and you can sort of, if you mark the insects, you can release them and you can start to hunt them, and they glow in the dark at night, and you can measure their forage and preference or their habitat preference. And again, we use these sticky traps. You can see in the upper left-hand corner, there's some BMSB eggs in there, and we shot these up into the forest canopy. And we also had some down at the lower canopy, so we're looking at height preference of foraging and habitat. And then we released these glow-in-the-dark wasps at night. We did this at 4 sites and had traps located at 16 locations. And initially, this was done in peach orchards and wood lines. And then we also sprayed the peach in the woods with different protein powders. So if we did catch any wasps, we could do some molecular tests later on and see if they had gone back and forth between both of them. So it's not just where we see them. We can collect them on those cards, on those sticky cards, and then see where they were previously as well. And we got some decent results. Total recapture rate was very small. That's typical in recapture. Only 2% were recaptured total out of the thousands that we released. But we did see that they did disperse into peach. And not only on the edge, they actually went pretty far into the peach. And that was some good. We repeated this experiment in the fall, and we repeated it in the peach line at Rutgers University, but we also wanted to do it in soy because I'm interested in field crops. Again, we put these sticky traps up in the woods, put them along the borders in soybean fields, and we released thousands of these marked wasps at night. But in the fall, we found extremely low capture rates. So low it's not even worth reporting, like 0.0001% recapture. So we don't know if there's something to do with the time of year that's important with their foraging abilities. So Ann and I are continuing this study at Rutgers University. We also want to see for field crops and orchards if we plant insectaries along field borders. The wasp adults feed on extrafloral nectaries. So if you have these insectary plantains, we want to see if that will retain the wasp population if you release them in those fields. Will they stay there, and will they provide biological control? So hopefully we'll have some more information on that at the end of this coming field season. And hoping this shows right now, this is our colony of our Trissolcus. So they're very, very small, minute wasps. And the reason basically why I'm showing you this is we see a lot of this stuff in our sweep nets, right? These small, minute things that we aren't really counting, but those are very important things in our systems that provide very important biological control, and that's why we want to move away from those calendar-based sprays, because you're also knocking down these good guys, these good predators that we have in our field. So, BMSB management challenges. I've told you all the bad news about BMSB and what it does to agricultural commodities. It's a season-long pest, so it comes out early in the year, in the spring, but it is all the way there until the fall. There's several generations, overlapping generations, and the nymphs and the adults cause economic damage. Again, they move between systems, so that doesn't make our insecticides very effective if there's not high residual capabilities. And even more frustrating is that they have this strong disturbance behavior. So our normal sort of sweep net calibration or scouting for this species of stink bugs can be difficult because as you're walking through those fields, they actually tend to drop off the plants, so you get an underestimation of the actual amount of bugs in the field. The USDA at Tracy Lesky's lab has been studying. They're one of the premier BMSB labs in the United States, and they did some pesticide insect tests, and they looked at 36 tests where they did these topical applications, and they would put the BMSB in these petri dish and monitor survivability. But they also looked at sublethal effects. So they have these ethovision, which is a camera that tracks movement, and they can see if these chemicals actually, even if it doesn't kill the bug, does it prevent them from moving and reduce possibly that they cause. So basically just want to show you that even within, it's kind of weird, even within insecticide classes. You have different classes here on these graphs. There's lots of variation. So some of them work, some of them don't work, and they're very specific to the Tracy Lesky's lab created this lethality index that basically the higher the number is, the better control you get. So those ones on the left side are the ones that are very good at knocking down BMSB, highly effective in the laboratory, and we found that in the field you sort of see the same thing. These are highly effective. These are the ones you want to use when you scout and hit threshold for. The good news is, as I said, it's an edge species, and it's probably an edge species because it's moving between different crops as it feeds. So it feeds on soy for a little bit, then it might go feed on wood, so it doesn't disperse too far into the soy field. And that allows us to provide some management without spraying the entire field. So several studies now have shown that a single border spray that's well timed can provide effective control. It's the same amount of control as spraying the entire field. But you're not knocking down pollinators, and you're obviously not hitting your natural enemies and causing secondary pest outbreak. If you look at Virginia Tech's extension page, they have done a lot of the threshold calculations for BMSB, for visual counts and sweep nets, and for beat cloths, and that is all online and available on their extension page. And they've also quantified, because of the disturbance with them falling off the sweep net, or the plants for sweep nets. And one of the newer ways that we're considering managing BMSB is with these insecticidal nets. So these are the same sort of nets that they use in Africa to control malaria, and they are impregnated with pyrethroids. And the thought was that you could put these nets up on the outside of your fields or around a specific tree in an orchard and hang those aggregation pheromone lures on it and attract BMSB so that they would land on the net and they would die. And this is a study that was done at the USDA where they baited some trees with these nets and basically monitored the damage. And they also did this on farms. And basically they said that long-lasting insecticidal nets attract and kill results look very good. So this is the grower standard on the left is in green, and that's the mean number of BMSBs in traps. So the attract and kill attracts a whole lot of BMSBs, but really you want to know fruit injury. That's what we're looking for, right? You don't really care when the take-home message as a grower is not how many you attract, it's whether the actual program works. So the graph on the right shows you the average fruit injury at harvest. And again, this is in orchards. And you can see when they use this attract and kill netting, it was far more effective at reducing damage in fruits compared to the grower standard, which is insecticidal full orchard sprays. The distance where you place the nets can be very important. Obviously, how far away from your fields is very important. These are not currently labeled for agricultural use, so that's why we wanted to test the question of how far away from your crop field do you need to place these nets. So the USDA did some field trials recently where they put the nets and the lures on the outside of the orchard. Then they put them on the border trees, so the first edge row of orchards, and then they compared that in the damage again to the grower standard of insecticidal threshold sprays. And what they found is that if you place those nets on the outside of your orchard, you get a lot of damage. So the spacing is extremely important, and that's something that we still have to refine and continue to work at determining. But if you place the lures in the nets on the border, that's in the middle graph, it's the same protection as you get from weekly sprays. And that's important because, again, you're not killing your natural enemies, and you're not having secondary pest outbreaks because of that. So at the University of Missouri and Wisconsin, we're further looking, and at the USDA, we're looking at whether we can use these nets in a field crop situation. So I have a graduate student that is starting to investigate this. Again, this is species specific, these lures that you place on this net, so you're not killing anything except brown marmorated stink bugs. And again, we don't have any of the data. We're still crunching the data for that, but hopefully this will provide some help in the future. Again, additionally, one of the things we're looking at is that you might be able to double stack lures on these nets also. So this could be nice. So you could hang Japanese beetle lures on it, and you could hang BMSB lures on it, and we wouldn't think that they would have any negative effect on attracting them. With that, I'd like to thank all of my collaborators, and again, a lot of this research came from other universities that I don't have on here. Again, I apologize for not being there in person. If you have any questions, please feel free to email me. My email address is up there, and again, I thank you.